Hello everyone, welcome to lecture 10 of Remote Sensing for Natural Hazard Studies course. So this lecture is on data type and remote sensing product. As previous lectures, this lecture is also divided into two parts. So this is the first part and this is the first lecture of module 4. This is potential of remote sensing in hazard studies. So today we will learn about the data type and remote sensing products which are available in public domain and some of them are paid. So let us talk about the data type. So before we go into the data type, let us talk about the digital images. We all know that images are of two types. First one is analog image, next is digital image. So what is the difference between these two? Analog images are produced using the pen, pencil, paper, whereas digital images, these are produced by electro-optical sensors, right. So here this is one example. So you will easily understand this is an analog image, this is a digital image. Now in remote sensing we are talking about the instrument based measurement. So here this is one example of satellite data. So here when we capture this image using any electro-optical sensor, when you zoom it, you will be able to see the pixels, right. So these are the pixels and these pixels are nothing but the digital number captured by your sensor, and these digital numbers are basically the reflected, emitted or back scattered energy from the target, right. Now when we see the data, when you try to import it in any programming language, you will be able to easily see the associated digital numbers. So these elements of this matrix are basically the pixel value of your image, right. So each pixel has an associated value known as digital number, the DN value, right. And here you can see this is one example how remote sensing sensors are capturing a particular area throughout the time, right. And this is examples of remote sensing data, how we are utilizing it. So we are able to monitor the glacial movement, we are able to produce the land use land cover. So these are typical example of remote sensing image application, right. And here this digital number, whatever we have captured, is basically helping you to extract the information. And remember, we have also discussed about the classification, that is how we are producing the land use land cover map. When we are going for continuous measurement, that means we have temporal images, we can have this kind of monitoring system, right. So these digital numbers are very useful in extracting the information captured by our sensor, and they are representing the target behavior, right. So when we say data type, so there are two major types. First one is the raster, next one is the vector. So here you can see the raster is basically having the pixels, right. So that is why the grid cell or pixel or the elements are present in this particular image, right. So this is the raster data, where the entire image or the data is divided into smaller portions or the parts, which is called pixels, and these pixels are the reflected, emitted or back scattered energies, right. Now when we talk about the vector data, so here you can see this is one line, it could be a road, or you can assume this is a river system, right. So these are represented with the lines, right. But some of the point measurement can be represented with this kind of point, right. So points are, so here you have points, here you have line, and the polygon, you can see here, this is one polygon, this is polygon. So, these three makes the vector data. Point map is also a vector, line map is also a vector, polygon map is also a vector, and you can have a vector map, vector data, which can have all these three, point, line and polygon together. When we talk about raster data, so the raster data, the area divided into pixels, as we discussed earlier, stores images as row and column of digital number for each pixel. Remember, we talked about when we export the image into any programming language, you will be able to see the background values associated with each pixel. So, these are basically your pixels and these numbers are stored, right. So, this is very important when we talk about raster data. It is stored in row and column of digital numbers. Digital output of any camera or sensor is raster data. So, does not matter whether you take the example of your handheld camera, your mobile phone images or any instrument which is capturing the image, that will have the raster data format. Based on the map, scale or spatial resolution, each pixel represent the area on the ground. So, remember we talked about this satellite, here you have sensor, sensor is basically the array of detectors, each detector is looking at the ground and then they are generating one pixel value, right, and these pixel values are representing the area on the ground, whether it is 30 by 30 meter or 40 by 40 meter, or if it is map scale, maybe 1 centimeter on the image is equal to 1 kilometer on the ground. So, this is called scale, right. So, this relationship you have to remember, the map scale or spatial resolution, that is represented by your pixel. Very useful in representing the continuous variation, thematic or dense data. Let us say I have a rainfall map, right, and this is one state for which I have generated. So, it is very ideal to use the raster data because it will show the slow variation in the values, right. So, that you will understand next in some of the examples. Very simple data structure, because here you have x, y and z. So, z is your basically dn value in case of satellite image, z could be your any measurement, it could be your rainfall, it could be your temperature, it could be your sea surface temperature. So, anything is possible to have it in z value, right. X, y will be fixed, that is your latitude, longitude. But when you store these images, these values, it requires large storage space, right, because we are storing them into JPEG, TIFF, GeoTIFF, these are commonly used data format, but we have HDF, right. So, this is very popular in storing the satellite images. Now, when we talk about the vector data, we have point, line and polygon. Now, when we talk about the point, this is the simplest element, here you have one value. So, this will have x, y location value and the z. Z can be any measurement that you have taken in the field, it can be again rainfall or precipitation, temperature, sea surface temperature, wind speed, anything you can store, or you can also have water table depth, you can have air quality, all these are possible to store against this one point, right. So, this is the simplest data structure. Now when we talk about the line, it is basically 2 points which are connected with a line, right. So essentially it will have 2 points, one will be starting, one will be ending. Here this is having 1, 2, 3, 4 points, and these are connected with lines. So minimum 2 points are required and maximum it can be anything, but it should not be enclosed. When it is enclosed, we call it polygon. So here it is starting point and ending point is fixed. Now here you can have n number of points in between, and here you can estimate the area. So if you have a polygon, you can estimate the area. If you have line, you can estimate the length of these 2 points or the distance between these 2 points. When you have point measurement, it is good for representing some of the values that you have captured in the field, right. So when we talk about this vector, area separated with different polygons. So the area here you can see this is separated with different polygons. Statistics can be estimated for individual line or polygon, because you can go for the perimeter estimation, you can go for area estimation. So all these are possible, and that is a very quick method. Very useful in representing the discrete data. Discrete means which is having very clear boundary, right. So let us assume this is a lake, this is a water body, right. So the water body will end at this particular line. So here if you have raster, for example, then what will happen? This raster may not match with the boundary of this particular lake. So in that case, this variation will not be shown properly. So in such cases, this vector is preferred, right. So that is the meaning of discrete data. When you want to represent the discrete data, you should have the vector data, right. Many attributes can be associated with each polygon. So let us say for this particular polygon, you have so many measurement. Let us say you have measured the water quality, or let us consider this particular lake. For this lake, you are going to have water depth, water quality, list of aquatic habitat, right. Then you can also have what is the status of suspended sediment, right. What kind of flora and fauna is present here, right. So those things can be listed against this particular polygon. Whereas when we talk about the raster data, this is divided into pixel, and here you can have only x, y and z values, right. But when you are having this x, y, z, z can be reflected, emitted, or maybe some measured values that you are having. But here this list is not limited to this. So here you can store maybe hundreds or thousands of parameters, right. So that's why many attributes can be associated with each polygon. It is not only polygon, it can be point also, it can be line also. Very complex data structure, because you are going to store many parameters and their relationship also needs to be stored. Whether this particular lake is inside this, right, or whether it is touching this particular boundary. So how system will record this? So that is why this structure is very complicated. Good representation of data or map requires small storage space, because this whole thing will be stored in the ASCII format, right. So this requires very less space. Now when we talk about the attribute, let us say that this is one map which is a vector data, right. So here you have all these polygons. So now here this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, right, and we have this table. So this is FID, so this is 1 to 8, this is ID, this is your ID that you have given to this polygon. Now we have also the information about the area. So the area can be estimated, so you can see everything is listed here. Now this is against 1, so this is 1, so this is ID 2, area is this much and the value is this much, right. For 2, this is ID 3, this is the area, this is the value. This is just for the example. Now here you see all these are recorded, and now if in future if you want to know what are the areas which are bigger in number, right. So in future if you want to run a query that show me the area which is greater than 4345 kilometer square, right. So except this, all these 2, 3, 4, 5, 6, 7, 8, 9 that will be highlighted, right. So here except this, everything is greater than this area. So similarly if you want to run a query that show me a land parcel which is costliest in this particular area, so it will automatically highlight this 8, ID 8. So this is 8, right. So though this area is small but it is costly. So such queries can be easily run on this particular attribute table. So that is the advantage of having the vector data. Now this is the third type of data which is called triangulated irregular network. So here you can see TIN is a vector based geographic data prepared by triangulating a set of points, treating them as vertices. So we consider TIN, triangulated irregular network, is neither a vector nor a raster. It is the intermediate data type. It is a digital surface and basically the morphological representation. The vertices are joined to form a network of edges. You can see the vertices are joined to form a network, right. There are interpolation technique used to construct these triangles, because these triangles are the surface for which data is not available. We have the measurement for this, this and this, but these are the places for which we are going to have the value using the interpolation technique, right. So here you see this is the edge, right, these are the faces and these are the vertices and this is the convection, right. Now when we talk about the TIN, it is good for representing 3-dimensional objects. So here 3-dimensional parameter that is good, like one of the best example is elevation. So using methods of computational geometry, the points are connected into what is called triangulation, forming a network of triangles. The lines of the triangles are called edges and the interior area is called the face or facet, right. So here you can see this is the interior. While the TIN model is somewhat more complex than the simple point, line and polygon vector model or the raster model, it is actually quite useful in representing the elevation. When we try to generate a digital elevation model, we are trying to represent the topographic variation of the elevation using the 2-dimensional images, right. So here when we are converting the 3-dimensional information to 2-dimension, where we have to be very cautious or very careful, right. So in such cases we will have more number of points measured in the field. So we can consider these are the points which are measured, and in between we could not measure, so we are going to have the interpolated values, and for that this triangulated irregular network is very useful. So there are different elements here. So the nodes, the fundamental building blocks of a tin. The nodes originate from the points and line vertices contained in the input data sources. Every node in the tin surface model must have a Z value. So here you should have the Z values, then only those values will be interpolated. The edges, every node is joined with its nearest neighbor by edges to form triangles, and here it should not cross, right. We cannot have this kind of triangle, right. Here the nearest point will be joined and then that will be making the triangles, right. So this kind of triangles we will be making. Each edge has two nodes, but a node may have two or more edges because edges have a node with a Z value at each end. It is possible to calculate a slope along the edge from one node to another, because once you have the elevation you can easily calculate the slope. So this is the first derivative, right. And now here we have connected all the nodes with these lines and we are making the triangles, right. And remember, as I told you, none of them are crossing each other. So all are having separate triangles. So now the triangles, each triangular facet describes the behavior of a portion of the tin surface. Now when we talk about this particular area, this particular triangle, this should have the closer value to these 3 points. This is not very close to this point. So if we consider this point to interpolate and derive the value of this triangle, that will not be correct. So that is why the nearest points are connected and they are used. The x, y and z coordinates value of a triangle, 3 nodes can be used to derive information about the facet, right, such as slope, aspect, surface area and surface length. So all these values can be easily determined using these 3 values. Hull, the hull of a tin is formed by one or more polygons containing the entire set of data points used to construct the tin. The hull polygon defines the zones of interpolation of the tin, right. Topology, this is very important, right. So topology, it is the structure of the tin which is defining the each triangle's node, edge number, type, adjacency to each other triangle. For each triangle a tin records the following information: the triangle number, the number of each adjacent triangle, the 3 nodes defining the triangles, x, y coordinate of each node, the surface z values of each node, the edge type of each triangle edge, right. So to understand this topology, let us make this map. Here you have one rectangle, then you have some ellipse, here you have a triangle, then here you have circle and then you have a point. Now how are you going to store? How this will remember that I am inside this, this and this, right. So this is topology. So the adjacency is recorded here, that is very important. And suppose in another case you have this kind of map, right, or maybe you can consider the state boundary. So this particular stretch of this particular polygon is common for this and this, right, but for this is the complete line. So this kind of record will be stored in terms of adjacency. So, it will also remember whether this boundary is shared between polygon 1 and polygon 2. This is shared between polygon 1 and polygon 3, right, and this plus this makes the polygon 1 boundary. So, all these will be stored. So, that is why when we say or when we compare this with vector data, the topology of tin is complicated, right. So, when we use the raster and vector data to represent our 3D surfaces, so let us understand what advantages and disadvantages we will have. So, when we talk about the raster data, it is basically the pixel, array of the pixel, right. And suppose when we are trying to represent this water body, you can see the shape is getting distorted because we are having the pixels here, and these pixels are not good for representing a discrete boundary, right. So, here if we have this, our lake will have this kind of shape, right, and this output channel will be like this, which is not correct. This is not possible in the surface, right. So, we can have this kind of flow of the water. It can be irregular, but it will be smooth, right. So, which is not possible with the raster data. When we try to represent this water body with vector data, it is properly getting highlighted. You can see this is the output channel. But when we are trying to represent this forest, the forest will not have this kind of sharp boundary, right. So, here with vector data, that is the limitation, because we cannot have the gradual changes, right. So, here what happens, you will have the sharp boundary. Now, when we go back to the raster data, these pixels are good for representing this forest because these are slowly changing, right. So, if you compare these two, both are having some advantages and disadvantages, but when we are talking about the real world, none of them are the true representation of the real world. So, what we do? We have to use both of them in such a way that they are representing the best of real world. So, then here you can see the forest is getting represented nicely. This is where we are using the vector data. So, this is properly represented, right, and here the other areas are also represented. So, when we compare raster and vector data, both are having some advantages and disadvantages. Depending upon what parameter or what value you are going to represent or what information you are trying to represent, you have to choose raster or vector data. But if you are trying to put many information in a single map, maybe you can use both of them together, and then your area will be having the best representation, right. Now, let us see some information about the digital elevation model, which is a very popular data product from remote sensing satellites. So, the digital elevation model represents height information in the z value, right, along with the latitude, longitude of the surface. So, as I told you that raster image, it is having the x, y and z value. Now, here x, y is latitude, longitude. Now, z, instead of digital number, we are having the elevation, right. So, once we are having the elevation, this kind of data is known as the digital elevation model, right. So, the digital elevation model represent height information in the z value along with the latitude and longitude of the surface, right. DM products such as slope, aspect, basin information, etc. are widely used in many applications, because once you are having the elevation, you can easily calculate the slope, that is the first derivative of the altitude or the elevation, Then aspect, what is the direction of the slope, it can be in the 0 to 360 degree. Then basin information, this kind of basin you can extract easily. So the most commonly used DMs are SRTM, Raster, ICNOS, GTopo30 and Cartoset. So these are available in public domain. You just have to make your login and then request for the data. These products are freely available, and you can have the elevation information about your surface, right. So there are different techniques by which we generate the digital elevation model. The first one is radar interferometry, second is satellite stereo pairs, then photogrammetry, laser altimetry and the contour lines. So the contour lines which is available in your topo sheets, that can also be used to generate the elevation information, right, because these contours are having the elevation information. So along these contour lines, this height is fixed, maybe it is 100 meter from MSL, this is maybe 80 meter, so this difference is 20, and then you can use this to generate your digital elevation model, and that can be used in your application, right. So one example of extracting the information from the digital elevation model is given here. You can see this is SRTM 90 meter DM. I am going to extract the digital elevation values along two lines, right. So the first profile is along this A and the second profile is along this B, right. So this is profile A, you can see this is 0, so 0 is here. Now along this line what we have done, we have extracted the values from this particular digital elevation model, those pixel values, and when you draw them, this is showing this kind of profile and you can calculate the slope, right. Here you can see height is in the meter. So this kind of information is very easily available when you are having a digital elevation model of your area. Now this is for profile B, remember. Now here when we see this digital elevation model, in general we use blue to red color profile. So here the red are basically the elevated areas. So I am suspecting that there is some elevation here, right. So these are some hills, these two, right. So now I am going to extract the information along this B line. So here you can see these peaks are coming and which is representing the hills of this particular portion, right. So this is very useful in representing or identifying the elevation profile or calculating the slope or the aspect, and it is very widely used in the hydrological application. So when we talk about the digital elevation model, we have the satellite image, then we have digital elevation model for the same area we can have, and once we have this, then we will have the better representation of the surface. So here you can see that satellite image and DM both are merged together, and then this is the 3D of that area, right. So here only the surface characteristic was available, here only the elevation profile was available, but when we merge them we can see the 3D effects, right. So with this I will end this part 1 and we will continue this lecture 10 with the next part, right. Thank you very much.